everyone. So today I'll be walking you through how we used model checking in order to help the development and ultimately verify properties of the SEL4 device driver framework communication protocol. So I'll first start off by running you through some properties of the sDDF, as well as the communication mechanism that's used between components in the framework. And hopefully this will be enough to motivate why model checking is such a great tool in this case. And I'll then run you through how we created our models, as well as the results that we were able to obtain. So the SEL4 device driver framework consists of a set of device drivers, as well as components which interface between those drivers and clients that all run natively on SEL4. So as well as this, it contains interface specifications, which demonstrate how components within the framework, as well as any client that wishes to use the framework, must adhere to. So one of the important design principles that was used in the implementation of the framework was a strict separation of concerns. So in terms of components within the framework, what this means is that each component is assigned a single task that's required during the processing of data from between device and client. So this is optimal for security and verification, as components are simple. However, it places an emphasis on the optimization of the intercomponent communication protocol. So the mechanism that we use for component communication is a combination of notification objects as well as shared memory regions. So the shared memory regions contain the data, which is being transported, but they also contain control structures that allow components to keep track of how that data is flowing through the system. And these notification objects are used to signal other components when data has been made available. So within the control regions, we have what we call sDDF queues. Now, sDDF queues are simple first in, first out queue data structures. And the way that a component is structured is it will typically be the producer of one queue and the consumer of another. So for a round of processing, a component will be removing work from one queue and then inserting it into another, and then finally notifying their neighbor. Now, what makes this mechanism so efficient is the fact that these queues have only a single producer and a single consumer. So this allows the data structure to be access lock-free. Now, final important note about these components is they're all event-based. So that means that they're blocked by default on their notification objects. And signaling will be required to enable each component to begin processing a queue. Now, this is enough background knowledge to understand what we mean by the signaling protocol. And this is the decision-making process that a producer goes through, as well as to determine whether it needs to signal a consumer. And we include within this signaling protocol any state information that a consumer publicizes to a producer to help understand whether the signaling is required. So during the development of a signaling protocol, it's typically a balance between eliminating any over-signaling, but also ensuring that you never have under-signaling. Now, over-signaling is basically any case where a producer signals a consumer, but there's actually no work that can be done. So a simple example of this would be when a producer is higher priority than a consumer, and it has enqueued some work for the consumer and signals, but then before the consumer has been able to be scheduled, the producer will preempt the consumer and enqueue more work and then signal again, when actually that second signal was unnecessary. Now, in terms of under-signaling, this is something that tends to happen when you start optimizing to eliminate any over-signaling. And of course, it's just when a producer does not signal a consumer, even when there's work to be done, and then the consumer is not scheduled to process that work. So at best, this can result in delays in data processing, but at worst, this can result in system-wide deadlocks. Now, the issue that we have with protocol development is that although each component is simple individually, there are many components within the system. So understanding the state of the system, where buffers are located at any particular time, can be extremely challenging. And this means that when deadlocks are experienced, it's very difficult to understand the sequence of events that resulted in the deadlock. But then also just with deadlocks, it's difficult to know if you've ever eliminated all of them entirely without using any sort of verification tool. So this is what brought us to the idea of using model checking. So luckily, my previous speaker has just introduced model checking. But the basic premise is that if you want to use a model checker on your code, you typically make a model using a different language, and that's a simplified version of your code, and that's passed to the model checker. And then under the hood, what the model checker will do is create a directed graph-like structure that represents your program. And then in order to verify properties about your program, the model checker will then enumerate all possible paths through this directed graph and ensure that each path satisfies the property in question. Now, if the property is satisfied, then the model checker will return true, which is great. But the good thing is, if it's not satisfied, it will return a sequence of events that led to the property being failing. Now, two major limitations we have with model checking. Well, firstly, any assurances that you get from a model checker are only as useful as how accurate your model represents your code. So, of course, care needs to be taken that the model is as accurate as possible. But perhaps the most annoying part of using a model checker is its extreme sensitivity to state space explosion. So, when you pass your model to the model checker, any additional state space that's included in this model can result in an exponential increase in the number of states in the graph that's produced. And then this can, of course, further increase the number of paths that must be enumerated and basically make proving anything impossible. So quickly, before I go on, we use Spin and Promella to create our models. And we also have only so far created models of the sDDF networking subsystem. Now, this is partially because it was the first subsystem that we actually worked on optimizing thoroughly, but as well as that, networking, of course, is highly sensitive to latency and has high data throughput requirements. So our first step was to take the code base as it existed and create Promella models of each component. So essentially here we were just trying to abstract away any state which wasn't directly relevant to the signaling protocol. And our first optimization here was to split the receive and transmit paths into separate models, as the components in each path did not rely on each other in order to make signaling decisions. So with this, we were able to find the deadlocks that we already knew existed, but we were also able to find the exact traces of execution that caused them. Now, with this information, this motivated us and allowed us to figure out a better way to create a new protocol. So we then created a simple two-component system with two queues and just experimented until we found some protocols that could work. And eventually we found three and implemented each in the C code and benchmarked to find which one was the most performant. So once we selected this one and we wanted to continue with the work, we then wanted to re-implement our Promella models using this signaling protocol to get assurances on a system that's actually modeling the networking subsystem. But unfortunately, we had a state space explosion problem. So in order to eliminate this problem, the first idea that we had was to use priorities. So priorities in Promella spin work in the same way as typical operating system priorities. The highest priority process that's not blocked is always scheduled. Now with this optimization, we were able to verify the receive and transmit path. However, these results were basically completely not applicable to a multi-core scenario where there's any possible interleavings of components. So we wanted to try something else that would allow us to have stronger results. So the next idea was to split each component, or split a system into, verify each component individually. So how we did this was to take as accurate a possible model of each component, but for the neighbors of that component, we only modeled the interaction that the neighbors had with the component to verify accurately, and the neighbors' interaction with their neighbors was a non-deterministic insertion and removal of packets. Now with this, we were finally able to have a result for each component in the subsystem. Now, in terms of the results of the signaling protocol, the protocol that we ultimately went with, that's still used to some degree, with only slight variance today, well, this protocol ended up being quite performant. So when we compare this protocol to the unconditional signaling protocol, which is when a producer signals a consumer each time work has been enqueued, well, you can see that the number of kernel entries in our protocol is significantly lower, but these kernel entries also include non-signaling kernel entries. So potentially a more helpful graph is the number of unnecessary signals. So these are signals where a consumer is awoken by a producer, only to find that there's no work to be done that has been given to it by that producer. So the columns on the left correspond to the sDDF signaling protocol, and the right are the unconditional. And you can see from the fact that you can hardly see any light blue that we don't have many unnecessary signals. Now, in terms of the future work, we hope to try and prove a stronger result that our Promella models actually are an abstraction of the sDDF C code. So this means that we want to show that any trace of execution in the C code is represented in a meaningful way in the Promella code. Finally, we hopefully would like to continue modeling other subsystems and model check other properties, not just about the signaling protocol, but currently we're working on correct accesses to shared memory using the C11 model. Okay, so thank you.